All right, today we're going to tackle a real classic, a problem from I.E. Irodov's famously tough physics collection. If you've ever been stumped by a collision problem, you're in the right place. Let's jump in.
You know that feeling, don't you? You're just staring at the page. You think you get the concepts, but connecting them to get an actual answer? It feels totally impossible. Trust me, you are not the only one who feels that way.
But hey, the only way to get past that feeling is to dive into the deep end. So that's what we're going to do. We're going to walk through this famous problem together, step by step. And we're not just going to find the answer, we're going to really understand why it's the answer.
So here it is, problem 1.175. Let's pull out the important clues. We've got two particles M1 and M2. M1 is moving, M2 is just sitting there. The key word here is the collision is elastic. That's a huge hint. And, this is critical, the particle that's moving is heavier. M1 is greater than M2. Our job? Find the biggest possible angle it can get knocked off course.
Okay, so let's picture the before shot. You've got mass M1 just cruising along with some velocity we'll call V1, and poor little mass M2 is just stationary, zero velocity. Right now, every bit of momentum and kinetic energy in this system is packed into M1.
And then, bam, here's the after picture. They've hit. Particle M1 glances off at some angle, and we'll call that angle theta. That theta, the deviation angle, is what we're trying to find. And of course, M2 gets sent flying at its own angle.
To crack this thing, we don't need anything super complicated. We just need two of the most powerful, most fundamental laws in all of physics. So let's get our toolkit ready.
First on the list, conservation of momentum. It's simple, really. The total amount of oomph the system has before the collision has to equal the total oomph after. But, and this is so important, momentum is a vector. It's got magnitude and direction. That's going to be key.
And tool number 2, conservation of kinetic energy. The problem handed us this on a silver platter when it said the collision was elastic. That's just physics speak for no energy is wasted. So the kinetic energy before has to equal the kinetic energy after. And unlike momentum, energy is a scalar. It's just a number, no direction to worry about.
All right, we've got our tools. Now for the fun part, using them to wrestle this problem to the ground and find our angle, theta. Don't worry, we'll go through it one step at a time.
Okay, step 1. Let's write down what conservation of momentum tells us. The initial momentum vector, which is just m1 times its velocity, has to be equal to the vector sum of the two final momentums. Simple as that.
Now for energy. Before the crash, all the kinetic energy is in particle 1. After, that energy gets shared between the two of them. We just write that down as an equation. The initial energy equals the sum of the two final energies.
You know, I've got to pause here and point out a classic mistake. It is so easy to just add the numbers for momentum and forget about the directions. Please don't do that. Momentum is a vector, and if you forget that, you'll end up in a world of hurt. It's probably the #1 mistake people make here.
Now here's the really cool part. Because those three momentum vectors have to add up perfectly, we can actually visualize them as a triangle. The initial momentum is one side, and the two final momentum vectors make up the other two sides. Seeing it this way, geometrically, is the real secret to solving this. So, it's time to do a little algebra. We're going to take our two big equations, momentum and energy, and mash them together. The main goal here is to get rid of the final velocity of the second particle, because honestly, we don't care about it. It takes a little bit of rearranging and squaring, but what comes out the other side is exactly what we need. And after the dust from the algebra settles, we're left with this gem. It's a single, powerful equation that connects the final speed of our first particle directly to that deviation angle, theta. We are so close now. So we have this relationship, but remember, the question didn't just ask for the angle, it asked for the maximum angle. So how do we squeeze a maximum out of this equation? This is where we need just a little bit of mathematical insight.
Well, if we shuffle our equation around a bit, it actually looks like a quadratic equation, from algebra class. And here's the thing about quadratic equations. For a physical collision to happen, the solution for the final speed has to be a real number, right? You can't have an imaginary speed. And that requirement, that the solution must be real, puts a hard limit on the values in the equation. And buried inside that limit is our maximum angle.
Think about that for a second. The rules of math are actually telling us about the limits of physical reality. Because the particle must have a real speed after it collides, the mathematics itself draws a line in the sand and says, the angle can't be bigger than this. It's pretty amazing.
And when we actually solve for that limit, this is what we get. The sign of the maximum possible angle is just the ratio of the masses. the target mass over the incoming mass. That's it. It's so simple and so elegant.
Now that's a beautiful formula. But what does it actually mean? What's the physical story it's telling us? Because a great answer in physics isn't just a formula. It's the intuition that comes with it.
Let's think of an extreme case. Imagine a huge bowling ball, that's our M1, hitting a tiny little p, our M2. The ratio M2 over M1 is going to be a number that's incredibly close to 0. So the sine of the maximum angle is almost 0, which means the angle itself is tiny. The bowling ball basically doesn't even notice the p and just plows straight ahead. It makes perfect sense.
And now you see why the problem statement was so specific about M1 being bigger than M2. Our formula tells us why. If M1 is bigger than M2, that ratio M2 over M1 is always going to be less than 1. And as you know, the sine of a real angle can never be greater than 1. So that initial condition wasn't just random, it was necessary for the whole thing to make physical sense. So what are the big takeaways from all this? First, for elastic collisions, your first move is always to use conservation of momentum and kinetic energy. Second, the ratio of the masses is king. It dictates the outcome. And third, we found this cool physical law. A heavy thing hitting a light thing can't just bounce off in any direction. There's a maximum angle, a cone of possibility that it's trapped in.
And that leaves us with one last question to think about. We solved the case for a heavy particle hitting a light one. But what about the other way around? What happens if a tiny pea hits a stationary bowling ball? Could the pea bounce back at any angle it wants, even straight backwards at 180 degrees? Based on the physics we just figured out, what does your intuition tell you? Give it some thought. Thanks for joining me.